I think electrons have a lot of untapped potential. Why? Well, here's a fun fact. If you wanted to take water, which consists of two hydrogens bonded to an oxygen, and split it apart into hydrogen and oxygen gas, you would need to heat that water up to 3,000 degrees Celsius. That's almost as hot as the sun. But if you take just two normal AAA batteries, you could split that water into hydrogen and oxygen with no problem. That's because the energy stored in a battery, or electrical voltage, is really good at pushing difficult chemical reactions forward. And you may not realize it, but our world is built on the products of difficult chemical reactions. From the clothes we wear, to the plastics we use, to the fossil fuels we burn, these all rely at some point on a difficult chemical reaction. Electrical voltage may just help us accomplish these reactions in more energy efficient and sustainable ways. For example, in the case of fossil fuels, the difficult reaction was the formation of the fossil fuels from carbon dioxide through thousands of years of natural processes. What if we could use the power of the electron to do the same thing, to make fossil fuels from carbon dioxide? Sustainable gasoline may sound like an oxymoron to you now, but perhaps the electron can help us get it done. I think the electron has so much to offer when it comes to making our planet more sustainable. Admittedly, the fact that we haven't just solved global warming by randomly hooking up batteries everywhere means it's not quite that simple. The thing is, electrical voltage is really good at pushing reactions forward, but sometimes it's too good and can also cause undesired reactions to occur. So, in addition to pushing the reaction with electrical voltage, we also need to guide the reaction, and we do this with something called a catalyst. What happens is the reaction occurs on the catalyst surface, and the catalyst guides the reaction by reducing energetic barriers along desired reaction pathways. But what is it about certain materials that make them good catalysts for certain reactions? I think this question is so fascinating, and more practically, answering it can help us design better catalysts. So in my research, I've been developing models that can help researchers both qualitatively visualize what is happening at these catalyst surfaces, and then quantitatively predict how the reaction will respond to different changes in the reaction environment. The conclusion so far has basically been that chemistry on catalyst surfaces is complicated, and a lot of the simplifying assumptions that researchers have traditionally thought to be true may not actually be correct. I hope that my research can help us build a more detailed understanding of these catalyst surfaces and help us realize the true potential of the electron. Thank you.